Okay, we are beginning chapter 3 now. In this chapter, we're going to look at this property of matrices called the determinant. And there's a lot of uses for the determinant that we'll actually see. But first off, we have to kind of define what it is and how to find it, and how you find it is somewhat dictated by the size, the order of the matrix you actually have. First off, if we have a 2 by 2 matrix, we'll go with our standard 1, 2, 3, 4. If we want to find the determinant, and we just abbreviate it, determinant A, you can also write that. Be aware though, that is not absolute value of A, it's just another shorthand way of writing determinant of A. The determinant can be negative, which is not like an absolute value. But to get the determinant, all we do in this case is, if we label this matrix A11, A12, A21, A22, the determinant is equal to A11, A22 minus A12, A21. We essentially find the product of the diagonals and then subtract them. But order is important, it's subtraction. So for this one right here, it would be 1 times 4, which is 4, minus 3 times 2, which is 6. And we get negative 2. Again, the determinant can be negative. And all things being equal, I mean, that's it. And it's really, really simple. If I have another matrix, negative 1, 5, 7, negative 2, I do the exact same thing. Negative 1 times negative 2 is 2, minus 7 times 5 is 35. I get negative 33, and I'm good to go. As far as it goes, obviously my determinant can be positive, negative, or 0. We'll see some things that occur based off of the type of solution you get, positive, negative, or 0. But for right now, that's pretty easy. It does mean, though, that if we're going to find these determinants, we need a few things. First off, you can only take the determinant of a square matrix. If it's non-square, I can't do this diagonal trick because there's no diagonal that cuts through the matrix. So I can only take the determinant of a square matrix. Keep in mind, I can actually do a 1 by 1 matrix. Say A is equal to the matrix 7, right there. That's a square matrix. It's 1 by 1, order 1. The determinant of that matrix is just the scalar itself, because there's the only number, there's no subtraction, there's nothing. Okay? And we'll see a more generalized formula later, like I said, for other matrices. The problem is, well, all things being equal, we're really not going to see 1 by 1s. I mean, they're essentially scalars. 2 by 2s, well, the determinant's incredibly easy. Multiply, multiply, subtract, and done. Which means a lot of times the trouble with determinants, or in finding determinants, is for higher order square matrices. 3 by 3, 4 by 4, and so on. And there is a formula for it, which we will go over. I would also encourage you, as I did in the last video, as these matrices get bigger, not necessarily a bad thing to just throw it into Maple or something like that and have it do all the calculations for you, because it can be cumbersome. Even if at first you just want to use it to check, to make sure you're calculating everything out correctly. I remember when I was a student, and keeping track of everything could sometimes become a challenge. So, if the technology is available, you may as well use it. But, suppose we have a 3 by 3, 4 by 4, and so on. We'll start with a 3 by 3 matrix. In order to calculate the determinant, first we have to find this thing, what's called minors and cofactors. And we'll have an arbitrary 3 by 3 right over here. We'll go with 1, 2, 3, 4, 5, 6, 7, 8, 9. And for our minors, we label them as M, I, J. It's the minor of the ith row in the jth column, one of the entries in the matrix. So for this one right here, let's see. We will say M21. And what that means is find the minor of the second row and first column. So second row, first column, that's right here. And now the way you find the minor, you cancel out that row and column from that entry. Now you find the determinant of the resulting matrix. So now in this case, I have a 2 by 2 matrix right here. Now I find the determinant of that using my trick for 2 by 2 matrices. In this case, 9 times 2 is 18, minus 3 times 8 is 24. 18 minus 24 is negative 6. For those of you who've taken Calc 3, and you might have seen it in some other classes too, but I teach Calc 3, we had to do tricks like this to solve out some of our cross products. We didn't really go into great lengths to explain why we did this in Calc 3. This is actually why we do it right here, because of these things going on here that we see in linear algebra. But I can pick a different entry, say minor 3, 2. That means this is going to get a little bit messy because I crossed everything out, but the matrix is pretty easy. Third row, second column, that's right here. I cross out the rest of that row and column. And now, again, it's a little bit hard to see, but the matrix that will be left over is 1, 3, 4, 6. And I find the resulting determinant. 6 times 1 is 6, 4 times 3 is 12, 6 minus 12 is negative 12. And there's my minor. We also have cofactors. And to write them in notation, cofactors are labeled Cij. And this is actually defined, this one I want to write out as negative 1 to the I plus j times mij. What that means is, to find the cofactor, or to find all the cofactors of a matrix, you find all the minors, using this idea right here, then you multiply it by negative 1 raised to the I plus j power. So for this one, we have those two minors, so now find C21 and M32. C21 is negative 1 to the 2 plus 1 times the minor 21, which is negative 6. M32 is negative 1 to the 3 plus 2 times the minor, negative 12. 2 plus 1 is 3. Negative 1 to the 3 is negative 1. Negative, negative gives positive. Negative 1 to the 5 is also negative. Negative, negative gives positive. And those are my cofactors. Once again, I referenced Calc 3. If you recall finding cross products, and we had this trick where we were randomly changing the signs of things as we multiplied everything out here. Well, if you recall, we had this weird little formula where for some reason we made the second term negative and things like that. And we didn't fully explain it there. But here now, well, if I think about a 3 by 3 matrix, just in terms of the sign of all the cofactors of a 3 by 3 matrix, all the even places will give me positives, all the odd places will give me negatives, meaning this is first row, first column, 1 and 1 is 2. First row, second column, 1 and 2 is 3. First row, third column, 1 and 3 is 4. Second row, first column, 2 and 1 is 3. And now clearly these will just keep alternating. And those will be the signs of my cofactors. Keeping in mind, there we're just referring to this negative 1 power, whether it will be positive or negative. The ultimate sign of the cofactor will also incorporate the value of the minor, and whether it's positive or negative. But again, if you've ever worked with matrices before, you see these little things like this that pop up, and sometimes, like in Calc 3, we just say, here's a formula, memorize it, there's a thing to it. This is actually the reason for it. This idea of minors and cofactors, which is not all that important to know when you're in Calc 3 and some other classes. You can just memorize the formula. But once we have this idea of minors and cofactors, now we can actually start looking at, well, how to find the matrix, how to find the determinant of a 3 by 3 matrix. And we have a formula. So, I want to write this in the same notation as the book, which is why I'm kind of checking this. So to find the determinant, if n is greater than or equal to 2, the order of the matrix is greater than or equal to 2, then determinant of A, which we can write like that, is equal to the summation j equals 1 to n of A1j C1j, which is equal to A11 C11 all the way out to A1n C1n. And we have this formula. Formulas like this should be pretty common now. We've seen lots of versions of them in different math classes. Couple of things to point out here. Here we are indexing with respect to J, which here, in terms of row and column entries for my matrix, I'm actually expanding this with respect to the column J. The I is actually staying the same, and in this case, it's actually staying as 1, which really means this is first row, first column, first row, second column, first row, third column, and so on. So all I'm actually doing here really is expanding by the first row of my matrix. And I'm kind of taking, say, the first row, first column, and then I find the first row, first column cofactor, using that trick we just had. Then I find the first row, second column, and I multiply by the first row, second column cofactor, and I keep on going all along the first row. So if we want to do this, suppose we have the matrix, here I'll just kind of mess around a little bit, 1, -1, 0, 2, 1, 3, -1, -2, 0, I don't know. So I have a matrix. I want to find the determinant of that matrix. Well, clearly, if I expand along the first row, it's going to be A11 C11 plus A12 C12 plus A13 C13. Add up those 3 entries right there. Now I just have to find them. C11, C12, and C13, I suppose I can do those right over here. C11 is -1 to the 1 plus 1, 2 times M11. C12 is -1 to the 2 plus 1, 3, M12. C13 is -1 to the 1 plus 3, 4, M13. So then let's see. C11, M11. If I want to find those, we'll put those over here. M11. I look at this entry right here. I cross out that column and row. I'm left with the matrix 1, 3, -2, 0. Now I find the determinant of this. 1 times 0 is 0. 3 times -2 is -6. And remember, it's 0 minus -6, which is 6. I'm going to need M12. So I do the same thing. First row, second column. I cross out this row and this column. I'm left with 2, 0. Have to write diagonal. 2, 3, negative 1, 0. 2 times 0 is 0. Minus 3 times negative 1 is negative 3. And I get 3. Then I need M13. Cross out this column and row. I'm left with 2, 1, negative 1, negative 2. 2 times negative 2 is negative 4. Minus 1 times negative 1 is negative 1. 4 plus 1 is 5. So now, C11 is negative 1 squared, which is 1, times M11, which is 6. C12 is negative 1 cubed, which is negative 1, times M12, which is 3. I get negative 3. And lastly, C13, negative 1 to the 4th is 1, M13 is 5, 1 times 5 is 5. Now, I can plug in. My determinant is A11, which is 1, times C11, which is 6, plus A12, which is negative 1, times C12, which is negative 3, plus A13, which is 0, times C13, which is 5. And I get 6, negative 1, negative 3 is positive 3, 0 times 5 is 0, and I get 9. Essentially, again, the idea here is take this entry right here, cross out that column in that row, find the determinant of the 2 by 2, and then multiply it by that entry here. Then, cross out this column and row, find the determinant, and multiply by this. And account for the negative of your cofactor, because that is 1, 2, sum of 3, negative 1 cubed. Again, to reference Calc 3, when we get our cross products, this term is always negative. That's why, because of this cofactor idea. Same thing here, cross out this and this, find the determinant, multiply by that. It's somewhat calculational in nature, but once you get the trick, well, it doesn't actually take all that long. More to the point, we want to do something else. My determinant is 9. So we can just say determinant of A equals 9. But we're going to mess with this a little bit just to make sure we're paying attention. I'm going to find the determinant using this row right here. The formula says use the first row, but I want to know what happens if I use the third row. The idea will still be the same. In this case, it'll be negative 1 times the cofactor of, let's see, this is first row, third row, first column, plus negative 2 times the cofactor of third row, second column, plus 0 cofactor of third row, third column. But now I understand this is just going to give me 0. 0 times anything is 0. So really I can just find those two. So cofactor 3, 1. That means I need M31. M31. Third row and column. Third row, first column right here. Negative 1 times 3 is negative 3. That gives me 0. So it's negative 3. M third row, second column. Here and here. 3 minus 0 is just 3. Now for my cofactors, cofactor 3, 1 is negative 1. 3 plus 1 is 4. Negative 1 to the 4th is 1, so that's negative 3. Cofactor 3, 2 is negative 1 to the 3 plus 2, 5 times 3. Negative 1 to the 5 is negative 1 times 3 is negative 3. And I get negative 1 times C31, which is negative 3, plus negative 2 times C32, which is negative 3. Negative 1 times negative 3 is 3. Negative 2 times negative 3 is 6. And I get 9, which is the exact same determinant as I got before. Which tells me, well, it kind of looks like I can use the first row or the third row to find my determinant. Could I use the second row? I'm not going to here, but yes, it's pretty obvious that it would work. As it turns out, you can use any row or any column to find your determinant, which kind of leads to a little, we'll say, trick or shortcut, if you will. I understand when I write out this formula, any entry that is a 0 will not be counted in my determinant, because I get that entry 0 times the cofactor, which is just 0. And if I can find my determinant in terms of any row or column, then it's probably best, given a matrix, to find the row or column with the most zeros in it and then expand around that row or column, because then multiplications will become 0 and calculating out the determinant will be easier. Bear with me 1 second. Okay, good. So we actually have a more generalized definition for the determinant of a matrix. And again, I want to write it the way your book writes it, so we'll use this one. Oh, we'll use the blue again. The determinant in terms of expansion by cofactors, which is just what we call it. If A is an n by n matrix, then the determinant of A is equal to the summation j equals 1 to n of aij Cij, which is equal to ai1 Ci1 all the way out to ain Cin. Meaning, again, I can pick any row I that I want on my matrix and expand along that row, whether I did in this case the first row or like we did the third row. I can pick any I want. Or I can do the same thing. I equals 1 to n of aij Cij, which is equal to a1j C1j all the way out to a nj Cnj. And now here again, this j is the column that I choose, first column, second column, third column, and then I expand along that column as I go from first row, second row, third row, all the way up to the nth row, etc. So I can pick any row or any column that I want. If I had some matrix that looks like 2, 4, 7, 3, 0, 0, 12, 5, 2. Find the determinant. Well, I'm going to expand around the second row right here. If I do that, I know it's going to be 3 times C, second row, first column, plus 0 plus 0. Now I just need to find one cofactor. C21 is equal to negative 1 cubed M21. Negative 1 cubed is negative 1. M21, if I cross out this and this, 8 minus 35 is negative 27. That's positive 27. And my determinant is 3 times 27, which is 81. And I can get the determinant really quickly. There is a rough proof in your book. I may actually have you sketch out a fuller proof later on, just for the fun of it, because it's a proof by induction, which is a fun proof to do. But if you think about it, we understand how matrices work. We understand we have elementary operations on our matrices. We understand that I can take the matrix and swap rows around. So sure, this is the second row, but what's to stop me from swapping the first row and the second row? Then the second row becomes the first row. Then I can just apply my definition to find the matrix of the determinant of the first row using my original definition. And since I know I can do that, then why would it matter? Why would I necessarily have to switch this up to here and then take the determinant using this expansion? Why not just leave it how it is and find the determinant that way? Which is essentially what's going on here. This idea that the determinant is invariant, it's always the same for all of these matrices, and it doesn't matter how you calculate it, as long as you calculate along a row or a column. One last trick, although there are other tricks, and your book points this out. There are other tricks to determine, say, the determinant of a 3x3, 4x4, etc. We have the basic definition, which is expansion by cofactors, which is the one I want you to be able to do, which is why it's the one I showed you how to do it. There are tricks. Your book mentions one of them, and I'm sure you can just Google and find other ones. If you want to learn those are completely fine. You need to be able to calculate the matrix out long form. Like I said, I'm deliberately only showing you this way, which is the standard way to do it. But yeah, there are other tricks you can pull out of the air. But just one last thing. Earlier, we were talking about upper triangular and lower triangular matrices. We said an upper triangular matrix has non-zero entries potentially along the diagonal, and the upper right triangle will say the lower triangle is always 0. So something like A11, A12, A13, 0, 0, A22, A33, A23, 0. That would be upper triangular, where you have zeros in the bottom triangle. Lower triangular is the exact same. A11, A22, A33, only I have zeros in the upper triangle. A21, A31, A32, and there we go. And then you can also have matrices that are both upper triangular and lower triangular. But if upper triangulars have zeros down here, lower triangulars have 0 down here, then if you combine both of these, the only non-zero entries in your matrix are along the diagonal. And so these are actually called diagonal matrices. And I will point out some of those entries could actually be 0. A, 1, 1, 2, 2, and 3, 3, same with the entries here and here. Those are not necessarily non-zero. They could be 0. But in order to be upper triangular and lower triangular, this part must be 0, this part must be 0. And again, if you have both properties, then everything is 0 except for along the diagonal, which can also potentially have zeros there as well. But now, suppose you have a diagonal matrix, or even an upper triangular one. We'll pick, let's see. We'll go with a standard 1, 2, 3, 0, 4, 5, 0, 0, 6. Find the determinant of that. Well, in this case, yep, still running. I'll check my time. Okay. In this case, I'm actually going to expand around here because there's the most zeros there. I could also use that column. But then let's see. I will get 6 times the cofactor 3, 3. Third row, third column. Which is 6, negative 1 to the 3 plus 3 times m3, 3. Negative 1 to the 3 plus 3 is negative 1 to the 6, which is 1. m3, 3. Well, if I get rid of this and this, then I just need to find the determinant of that. 1 times 4 is 4, 2 times 0 is 0. That's just 6 times 4, which is 24. And I'm done. But the trick here is, well, 6 times 4? That's really just that right there. 1 times 4 times 6. And as it turns out, you can also pick a 2 by 2, pretty easier to see, 1, 2, 0, 3. What's the determinant? 1 times 3 is 3, 2 times 0 is 0. I get 3, which is again the product of those diagonals. And what it means is, if you want to find the determinant of an upper triangular or lower triangular, or by extension, diagonal matrix, as it turns out, the determinant is just the product of the numbers along the diagonal. And yes, that means if one of the terms along your diagonal is 0, then your determinant will be 0. But it means, again, we have the general formula, and here we actually used the general formula. I picked the nicest row possible, set up the general formula, plugged in, got my determinant. But as it turns out, in this case, if I have upper or lower triangular, or by extension diagonal, I don't have to do that. I can just find the product along the diagonals. So we have this simple rule for determinants of 2 by 2s. This times this minus that times that. When I expand to 3 by 3s, 4 by 4s, etc., I have my general formula. And I also get these tricks if there are different properties of my matrices, if they're triangular, diagonal, whatever. We are going to continue working with these determinants. Again, they are really important properties of matrices, so we're going to spend more time working on them. Right now, we just start, much like with calculus and derivatives and integrals, with the ability to actually calculate them out, and then we'll go from there and see some of their uses.